we have discussed the global Pareto set. Now we will see the local Pareto set. So as we can see here, the definition 4 says that if for any member X in a set P there exists no solution. So this particular solution we are assuming in the neighborhood of the X such that the gap, so y minus x norm infinite is smaller than equal to epsilon value. This epsilon, if we are taking a small value, small positive number. So if there is no solution which is dominating any member of the set P, then solutions belong to the set P constitute a locally Pareto optimal set. If we look into the figure here, as we can see, we have two objectives. We want to minimize both the objectives. So let us take the local Pareto optimal set. So if we take a solution A, so if we are going to perturb this particular solution in the neighborhood, so then there is no solution which will be dominating the A. Similarly, the other solutions which will be lying on this particular set. Same thing can happen with the another local Pareto optimal set. Since we are comparing in the neighborhood only, so therefore it is called as local Pareto optimal set. Now we will discuss the strong dominance and weak Pareto optimality. It is only because the dominance relation which we have come across, that is still a weak. Why? Because the notation which we have used, that has something similar to smaller than or equal to. So if we look into the strong dominance relationship, so as we can see here, the dominance relationship between any solutions earlier that we have found in equation number 2. So equation number 2 is the relationship for the concept where we use concept of dominance, that we consider as a weak dominance. So the definition 5 suggests that solution x1 strongly dominates solution x2, meaning that, as you can see, we are using this notation, and earlier with that we have a equality as well. So here it is a strong domination. So x1 is strongly dominating x2 if solution x1 is strictly better than solution x2 in all objective. So that suggests that if I am comparing two solutions, say x1 and x2, and at the time when we are comparing the f1 objective and f2 objective, so in this case the f1 value as well as f2 values, both the objectives for x1 solution are better than the x2 solution. In this case, we can say that x1 is strongly dominating x2. Now we have a weakly non-dominated set. Suppose among a set of solution P, the weakly non-dominated set solutions P bar, P prime are those that are not strongly dominated by any member of the set P. So meaning that when we are using the concept of a dominance and when we are trying to compare each and every solution, in this case, since the relationship, the dominance relationship which we have understood earlier, if we are using it, then there are some set of solutions that when we are following the definition of the concept of a dominance, they are not weakly dominated by the other members of the P. Under the dominance and Pareto optimality, now let us discuss the spatial solutions. We will start our discussion with ideal objective vector. So let us see what is the definition. The mth component of the ideal objective vector. So we are saying we are representing it as a Z star is the constraint minimum solution of the following problem. Now here, suppose we are minimizing one of the objectives subjected to the various constraints. So the solution which we are going to get it, that will construct the ideal vector. So suppose when we are minimizing the above problem, the solution is x m star and its function value is f m star. So what is ideal vector? So Z star is represented as, so f1 star means this is the minimum function value when we are minimizing equation number 3 with respect to f1. Similarly, f2 when we are minimizing again the equation 3 with respect to f2 and so on. So the minimum objective function value when we are independently minimizing f1, f2 then up to fm, the vector which we are going to get in terms of their objective function, it's called the ideal vector. Let us look at the figure on the right hand side. Here we are minimizing f1 and minimizing f2. In this case, if suppose we are going to minimize say f1, if we minimize it, so this is the point which we are going to get it. So let us take this is as a f1 star. Similarly, when we are minimizing f2 independently, we are going to get the another point, that is f2 star as per our definition. So in this case, Z star, which is the ideal point vector, will become f1 star and f2 star. So that is the ideal objective vector for the given problem. Here it is important to note that this particular vector is non-existence. Why? Because as we have understood when we discussed about the multi-objective optimization properties, so one of the properties is that the objective should be conflicting in nature. Now since when we are minimizing say f1 independently and then when we are minimizing f2 independently, we are going to get a 1 point. Since f1 and f2 are conflicting in nature, what we can understand is if we are going to minimize f1, then at the same time the value of f2 will be more. So we have to compromise in the f2 value, and vice versa. When we are minimizing f2, then we have to compromise with the f1, and that result in a set of Pareto optimal solution. If we minimize both the objectives and these objectives are not conflicting in nature, so as we remember, the solutions will converge to a single solution. Here we have taken an example of conflicting objective as we have seen in the figure. So this means that if I am independently minimizing f1 and f2, the resultant vector which I get in terms of f1 star and f2 star, so that particular value we cannot achieve. So that's why it is called non-existent vector. Now let us move to the another solution, that is called utopian. So as we can see in definition number 8, utopian objective vector. This particular vector is represented as a Z star star, and this vector has each of its component marginally smaller than that of ideal objective vector, that is Zm star star equals to Zm star minus epsilon m, with epsilon for all the objective. When we are presenting this particular definition, we are assuming that we are minimizing all the objectives. If we look into the figure on the right hand side, so here this figure, so this Z star we have already identified. Now when we are going to subtract epsilon in F1 and epsilon in F2, we are going to get a point Z star star, that is an utopian objective vector. Again, this particular vector is a non-existent solution for a multi-objective optimization. The third kind of a solution which we know is called Nadir point. So, let us see that. So, the Nadir objective vector, as we can see, it is represented as Z NAD, that represents the upper bound of each objective in the entire Pareto optimal set. So, this is an important line where we are saying it is the entire Pareto optimal set. So, let us look into the figure on the right hand side. So, this particular red line is the Pareto optimal set, and if we look at the corner, so this is one of the corner and this is another corner of the Pareto optimal set. So, when these 2 points are constructed and using these 2 points, we are going to find the Z Nadir. So, this is the Nadir point here. So, this particular point should not be confused with the worst point, which is represented by W here. How we are getting W? Suppose I want to maximize F1. So, if I maximize F1, I am going to get this particular point, which is F1 max. Similarly, if I independently maximizing F2, I am going to get this particular point, which is represented as F2 max. Now, as you can see, the component of a W is represented by the F1 max and F2 max. So, therefore, we should be clear about what is the difference between the worst point and the Nadir point. So, as again this Nadir point we constructed with the help of the extreme solutions of the Pareto optimal set. However, the worst point W, it is different. It is corresponding to the worst objective function value of the feasible region. So, the particular figure which we have shown here, that is help us to understand that if we are going to maximize say F1 and then independently maximizing F2, it will give me the worst point rather than the Nadir point. Now, the question comes that these spatial solutions starting from the say ideal point, utopian point and Nadir point, and we have one more point called worst point. So, what is the significance of these points? As we can see in here in equation number 4, these spatial solutions are required to normalize the each objective. How we can do it? So, suppose Fm norm, so I am talking about the mth objective, this we can normalize as the objective function value Fm minus the mth component of the ideal point divided by the mth component of the Nadir point minus, and this should be small m. So, this should be the mth component of the ideal point. So, what you can see here is when we are going to use, for example, ideal point and Nadir point, so the objective function value will be lying between 0 to 1, for example. In this case, suppose we are solving a problem in which F1 objective value is given in terms of 10 to the power 6, and if we look at the value of F2, it is lying in terms of say 0.1, 0.2, 0.3. So, there is a huge difference between the values of F1 and F2. If we are going to solve this particular problem, then our EC techniques can prefer F1 over F2. In order to have an unbiased search, we normalize both the objective. Whenever we normalizing it, f1 will be lying between 0 to 1 and f2 will be lying also 0 to 1, and in that case the selection criteria for our EC techniques will make emphasis to both the objectives, and that is why we normalize our objective function when we solve a multi-objective optimization problem. So, in this particular session we have come to the closer. Here we started with the introduction where we understood the definition of multi-objective optimization. Thereafter, a very few practical examples we have gone through to understand that this multi-objective is so common in nature that the problem which we solve or we handle, that are also sometimes multi-objective in nature. After that, we discussed about the approaches to multi-objective optimization, where we understand about the preference based multi-objective optimization, in which we convert the multi-objective optimization problem into single objective optimization. Then we discussed about the ideal multi-objective optimization approach, in which we can generate multiple optimal solutions, and then finally we are going to select one solution using some higher information. Thereafter, we also discuss the role of EC for solving the multi-objective optimization problem. Thereafter, we discussed about the problem formulation in multi-objective optimization, the principles. Under the principle, we talk about Pareto optimality, the two goals that we have found in multi-objective optimization, then the non-conflicting objective which we discussed, and we also understood what will be the difference between single and multi-objective optimization. And finally, we discussed about dominance and Pareto optimality. There we started our discussion with the concept of a dominance, where we have shown the relationship. Then there are certain properties which we have discussed, symmetric, asymmetric, and etc. other properties we discussed. We also discussed about the Pareto optimality, the global Pareto optimal set, the local Pareto optimal set, that we have undergone through it. We also discussed about the strong dominance and weak Pareto optimality in order to find the solution is strongly dominating the another solution. And finally, we discuss about the spatial solutions. These spatial solutions such as ideal vector, utopian vector, nadir point and the worst point. These points we use it to normalize the objective functions. With this introduction, I conclude this session. Thank you very much.